Okay, now we're going to take an in-depth look at our routing table. Keep in mind this topology here on the right, we're going to refer back to it several times. Um, we're going to look at the routing table as it pertains to this particular topology. The routing table hierarchy in Cisco IOS was originally implemented with classful routing scheme, and although the routing table incorporates both classful and classless addressing, the overall structure is still built around a classful scheme. So if you do the show IP route and we begin at the gateway statement, this is what we're going to look at. We're going to look at the routing table. You'll notice here that the routing table of router 1 contains 3 directly connected networks. And notice that 2 routing table entries are automatically created when an active router interface is configured with an IP address and a subnet mask. Okay, so what we see here, you see the route source, the destination network, and the outgoing interface. The legend here for our route source, it identifies how the network was learned by the router. It identifies the destination network and how it's connected, and the outgoing interface identifies the interface on the router connected to the destination network. So this is information that we gather here from this location. Now in our routing table, we can see different lettering over to the left. That's our route source. The S identifies that the route was manually created. It's a static route. D identifies the route was learned dynamically from another router using EIGRP. O identifies the route was learned dynamically from another router using OSPF, and R indicates that it was learned using RIP. So as we take a closer look here, we have our route source. It identifies how the route was learned. You have your destination network that identifies the address of the remote network. Then you have your administrative distance. It identifies the trustworthiness of the route source. You have the metric that identifies the value assigned to reach the remote network, and lower values indicate preferred routes. Then you have your next hop, and it identifies the IPv4 address of the next hop or the next router to forward the packet to. Then you have your route timestamp that identifies from when the route was last heard. Then you have the outgoing interface, and that identifies the exit interface to use to forward a packet toward the final destination. So a dynamically built routing table provides a great deal of information. As we see here in this one, it's crucial to understand the output generated by that table so you understand what's going on. And the Cisco IP routing table is not a flat database, so keep that in mind. Your routing table is actually a hierarchical structure that's used to speed up the lookup process when locating routes and forwarding packets. Routes are discussed in terms of ultimate route, level 1 route, level 1 parent, and a level 2 child route. The ultimate route is a routing table entry that contains either a next hop IPv4 address or an exit interface. Directly connected, dynamically learned, and local routes are ultimate routes. Okay, so in this figure, the highlighted areas are examples of ultimate routes. Your static quad 0 route, then the ones who are directly connected are also those that have been learned, dynamically learned. Your level 1 route is a route with a subnet mask equal to or less than the classful mask of the network address. Okay, so you have a network route, you have a supernet route, and a default route. Your quad 0 is a default route. You'll notice here that it has a network route and a supernet route. Here is our static route. Here is our super route. This is the level 1. So we have our static, and this one is a SuperNet. See here? Default, SuperNet, network. Default, SuperNet. Now our level 1 parent route is a level 1 network route that is subnetted, and a parent route can never be an ultimate route. Okay, it can't be because it's a parent, it has more to it. Here we have highlighted the parent 1 routes. So up here was the static route earlier. Then we have our parent. It's 172.16.00.16. It's variably subnetted. There are 5 subnets and 3 masks used. Again, here we have it subnetted. There's 5 subnets and 2 masks. So you know that that is the parent route. The level 2 child route is a route that is a subnet of a classful network address. So here we have our parent route, and the parent has a child route. So here's the parent route on the network. Here's the child route. It's the subnets. And here you see them also. It's connected. It's directly connected. These are ripped as well. Now, when your packet arrives at the router interface, it's going to look at the IPv4 header. It identifies the destination IPv4 address and proceeds through the router lookup process. First, it's going to look for, is the best match a level 1 ultimate route? If it is, then it goes out that way. If the best match is a level 1 parent route, it proceeds to the next step. If there's a match with a level 2 child route, then the subnet is used to forward the packet. If there's not a match with any of the level 2 routes, it proceeds to the next step, which then, if there's now a lesser match with a level 1 SuperNet or default route, the router uses that route to forward the packet. And if there is not a match with any route in the routing table, it drops it. Okay? So we go for level 1 routes. If we see it there, it uses it. Then it drops down to the parent and child. And if it can't find anything in the SuperNet or the default, it's dropped. So with our IPv4 route lookup process, what it's doing is it's going to match between the destination IP address of the packet and the route in the routing table, and a minimum number of far left bits must match between the IPv4 address of the packet and the route in the routing table. The subnet mask of the route in the routing table is used to determine the minimum number of far left bits that it must match. Okay? So remember that IPv4 packets only contain IPv4 addresses and not the subnet mask. Okay? So the best match is the route in the routing table that has the most number of far left matching bits with the destination IPv4 address of the packet. The route with the greatest number of equivalent far left bits or the longest match is always the preferred route. Now, our IPv6 routing tables are very similar to the IPv4 routing table. It's populated using directly connected interfaces, static routes, and dynamically learned routes. The topology that we're displaying here is the one we're going to look at next. EIGRP for IPv6 has been configured on all these routers, so that's what we're going to look at. So when we do our show IPv6 route, we get the information shown here. The highlights here are the connected networks and local routing table entries of the directly connected interfaces. The 3 interfaces were added when the interfaces were configured and activated. So you have your route source, your outgoing interface. Here is the directly connected network. You have your administrative distance and your metric. Okay, so our source, the directly connected network, the administrative distance, the metric, and the outgoing interface. One thing to note is that the serial links have reference bandwidths configured to observe how EIGRP metrics select the best route, and the reference bandwidth is not a realistic representation of modern networks. It's only used to provide a visual sense of link speed.